For a three-dimensional stress state, the procedure must be adapted as follows. To do this, it is necessary to solve a cubic eigenvalue problem. The corresponding heuristic equation is obtained by evaluating the determinant of this expression. The coefficients I1, I2, I3 represent the first three stress invariants of the stress tensor sigma. These invariants are independent of the chosen coordinate system and are computed as follows. By solving the eigenvalue problem, the principal stresses are obtained. These principal stresses are then used to construct the three Mohr circles. Solving the eigenvalue problem also yields the eigenvectors, which define the directions of the principal axis. Using Mohr circles, it is now possible to determine the components of the stress vector T graphically for the three-dimensional stress state. The stress vector T describes the action of the stress tensor sigma on a given cut surface. The surface is oriented orthogonally to the normal vector n of the cut plane. Through Cauchy's stress law, this relationship can also be computed analytically. To define the normal vector n, LEMOHR uses the concept of space angles. Space angles can be visualized as cones around an axis, where the angle between the cone surface and the axis corresponds to the space angle. If this principle is applied to all three axes of the principal axis system, a common intersection line may result. To ensure a unique intersection line and thus a unique normal vector n, LEMOHR computes a coherent combination of angles in the background based on the user-defined space angles. Given the angles alpha 1 relative to the 1 axis and alpha 3 relative to the 3 axis, Mohr circles can now be used to determine the stress vector T associated with the space angles and the corresponding normal vector n. In the black circle of the 1-2 plane in the principal axis system, starting from the principal stress sigma 1, twice the angle alpha 1 is plotted counterclockwise. This yields the point on the black circle. Starting from sigma 3, twice the angle alpha 3 is plotted clockwise on the turquoise circle of the 2-3 plane. This yields to the turquoise point on the turquoise circle. Using the center of the black 1-2 circle, an arc is drawn from the turquoise point on the turquoise circle. A second arc is drawn from the black point on the black circle, using the center of the turquoise 2-3 circle. These two purple arcs intersect at the point T. The sigma component of this point corresponds to the normal stress component of the stress vector T, in other words, the stress acting perpendicular to the selected cut surface. The tau component represents the combined shear stress acting in the green highlighted cut plane. To uniquely define the normal vector n, exactly two space angles or equivalent information are always required. To determine the stress vector geometrically from Mohr circles, exactly two space angles are also required. At the same time, there are three space angles from the principal axis to n, of which only alpha 1 and alpha 3 have been used so far. Using any other valid combination of angles that leads to the same normal vector n will yield the same components of the stress vector T from the Mohr circles. Here, the procedure is shown for alpha 1 and alpha 2. The key takeaway: for a three-dimensional rotation, the point T lies in the region between the Mohr circles. For a rotation within one of the three principal planes, the point remains on a circle contour, shown here for a rotation on a 1-2 principal plane by 66 degrees measured from the 1 axis. A uniaxial stress state with a single normal stress produces a three-dimensional strain state. This follows directly from Hooke's material model. LEMOHR allows the user to manipulate the material parameters. With a higher Poisson's rate, the material undergoes stronger lateral compression. This also makes it possible to understand the influence of the scaling factor used for visualization. A shear stress produces only a shear strain, and in this way, the strains associated with three-dimensional stress states can also be understood. LEMOHR also helps in understanding the failure theories. Failure theories provide a unified way to assess the strength of components under uniaxial and multi-axial loading. Material properties are typically obtained from uniaxial tensile tests on standardized specimens. For multi-axial stress states, these failure theories define rules for reducing such states to a single quantity, the equivalent stress, which can then be compared to the maximum allowable stress. Which failure theory is used depends primarily on the material behavior. According to Rankine, The normal stress theory applies to materials that fail in a brittle manner. If the largest principal stress in absolute value is smaller than the allowable stress, failure at that point in the component is not expected. The allowable stress is the quotient of the ultimate tensile strength, the stress at which fracture occurs, and the chosen safety factor. The required principal stresses can be conveniently read from the stress diagram. According to Tresca, for materials that fail in a ductile manner, the decisive quantity is the maximum shear stress, more precisely twice the maximum shear stress. This shear stress always lies on the Mohr circle of the 3-1 plane at an angle of 45 degrees relative to the principal axis system, in other words relative to sigma 1 and sigma 3. This is the maximum shear stress theory. The orientation of the failure planes in an infinitesimal cube can look as follows. In red, for brittle failure, the plane is perpendicular to the 1 direction, where sigma 1 is larger in magnitude than sigma 3. In green, the failure plane according to the shear stress theory. The more detailed distortion energy theory according to von Mises also describes when ductile materials fail. Here, failure is not determined by the maximum normal stress or shear stress alone, but by the combination of all stress components at the material point. Since failure in a real component can occur on multiple planes, this theory does not yield a single unique failure plane. However, the distortion energy theory does define a failure surface. These representations show the principal stress space, with sigma 1, sigma 2, and sigma 3 as the axis. The principal stress space must not be confused with the principal axis system. It is merely an abstract space. Each point in this space corresponds to a stress state at a material point. If the point representing the current stress state lies inside the bounded region, failure is not expected. According to the shear stress theory, the left prismatic shape forms the failure surface. According to the distortion energy theory, the right cylindrical surface results. Both bodies extend along the hydrostatic axis, where all principal stresses are equal. Viewed perpendicular to the hydrostatic axis, it becomes clear why the von Mises failure theory is somewhat more accurate. All combinations of principal stresses lying outside the hexagon would, according to Tresca, indicate failure. However, all points lying between the golden circle and the black hexagon would be incorrectly excluded by Tresca, but correctly allowed by von Mises. The same conclusion is reached when the principal stress space is shown only in the sigma 1, sigma 2 plane. According to Tresca, no failure occurs as long as the point lies within the gray region, which is bounded by the yield stress as shown. According to von Mises, this plane, as an oblique cut through the cylinder, yields an ellipse, which encloses a larger area than the Tresca region. This additional area means that more combinations of principal stresses are permissible before failure occurs at that point in the component. LEMOHR is available free of charge for everyone via the installation link provided in the description. There you will find a file that can be used directly within the Metal program, which must be installed beforehand. Alternatively, on a Windows operating system, the standalone exe file can be launched. A double click on the exe opens the installer, where you click on Next, check the box, add shortcut to desktop, and then click on Begin Install. The installer can then be closed via Close, and LEMOHR can be started using this icon on the desktop, which takes about 30 to 60 seconds to load. Enjoy!